It is the 20th. Okay. Let's leave it. Okay, Amway's not here. Bessie is here. Bishop here. Bragg not here. Caudill is here. Chestnut not here. Goldwood not here. Erlinson not here. Gerard not here. Green not here. Kennedy not here. Leonard is here. It's online. Mohammed Boy not here. Small not here. Sullivan is here. And Swissack not here. All right. So we're finished with chapter 4. And we're going to get into chapter 5, which deals exclusively with gases and what we deal with them, especially when it comes to reactions and so on. All right. Right? This is too cold for this place. Yeah, unfortunately, I can't.
Is there a handout for chapter 5?
Yeah, I'm gonna hand it over shortly.
Okay.
After we discuss a couple of things. So again, chapter 5 is gases and it deals with topics that you learned before in your introductory or general chemistry. And therefore, I'm going to try to go through it rather quickly. But some stuff will be repeated. In fact, most of the stuff will be repeated from what you learned before. So, all right. So gases, what are they? More to the point, what are they like? Well, if you look at gases at the microscopic level, at the level of atoms and particles, basically consist of those particles moving around randomly. Most of their movement would be straight line motion, and they'll be deflected from that straight line motion if they come into contact with other gas particles or the container itself, the walls of the container itself. So because they collectively or individually display this sort of behavior, collectively they impart certain properties that we are all familiar with associated with gases. For example, gases flow readily and they will occupy the entire volume of their container, right? And that's a consequence of the fact that the particle is always moving, always having high kinetic energy and so on. From time to time, you'd hear the term vapor, which is usually reserved for a substance, which is normally a liquid under room temperature conditions. But if you elevate the temperature of it, then it becomes a gas, right? So that gas is called a vapor. So people talk about water vapor or ethanol vapor or methanol vapor, right? But when it comes to gases that exist as gases under normal room temperature condition, we simply call it gases like oxygen, hydrogen, nitrogen, and so on, right? And the last point being made here, and that's in reference to what we said about vapors. Many low molar mass molecules or molecular compounds actually exist as gases or easily vaporizable liquids, all right? So carbon dioxide is an example, water is an example, and so on. And here we have a list of different gases and their uses. I won't go through all of them, but you can read this on your own. So this is just to indicate that not only do we study gases because we're interested in them inherently, but we can actually use gases for certain purposes, right? Okay, so let's talk about the kinetic molecular theory. This is a model that is used to basically explain what we observe as far as the properties of gases are concerned, right? So as I said before, the theory basically states, or the assumption that is made, is that the gas, if you have a gas in a container like a flask, as shown here, then the particles of the gas are always moving because they are high energy. And as I said before, they tend to move in straight lines. The term for that is translational motion. But of course, they can be deflected from that motion if they hit each other or if they hit the walls of the container, right? So based on our understanding of the behavior of gas particles at a microscopic level, we can relate that to certain properties that gases will exhibit. For example, everybody knows that a gas will exert pressure on the walls of the container that they're in. And that can be explained based on the kinetic molecular theory, in that basically what happens is that the particles, as I said before, are high energy, always moving, and they will hit the walls of the container continuously, and therefore exert forces on the inner walls of the container. And that force is basically transmitted or translated into pressure. And later on, in fact, very shortly, we're going to learn the difference between pressure and force, right? They're two different things, even though they're related. Also, again, we can understand, based on the kinetic molecular theory, the relationship between temperature and pressure, right? Again, we all know that if you increase the temperature of a gas, the pressure would increase. Why is that so? Because when you increase the temperature of a gas, you're imparting energy to the gas particles. The gas particles will move around faster. They will hit the inner walls of the container with more energy and more frequently, and that would result in an increase in pressure exerted by the gas on the walls of the container. So we're going to look into all of these in more detail later on in this chapter, all right? So let's talk about pressure. I referred to pressure earlier. Let's define what we mean by pressure. Pressure by definition is the force per unit area, all right? And there's a formula that can be used, which is P is equal to F divided by A, right? P is pressure, F is force, and A is area. And as stated here, the force is expressed in newtons according to the SI system, and the area will be expressed in square meters, all right? Now, as a result of that arrangement as shown in this equation here, the units of pressure can be expressed as newtons per meter squared. But there's a special name given to this collection of units. It's called the Pascal, right? So the Pascal unit is the same thing as newtons per meters squared, all right? And then you can have larger units like the kilopascal, which is most often used based on the fact that the Pascal unit is a relatively small unit, right? Okay, so there are other units, excuse me, of pressure. You have the atmosphere unit, which is not an SI unit or metric unit. And then you have the millimeter mercury unit, which is the same thing as the torr unit. Those are used as well, all right? And then we can convert from one unit to the next because there's actually relationships between these units, which is shown on this slide right here, right? So here we have the units. We have one atmosphere here, which is equal to all these values here expressed in different units. One atmosphere is equal to 760 millimeters mercury. And I'm going to explain how this number was arrived at experimentally. And that is the same thing as 760 torr, because the millimeter mercury unit and the torr unit are both one and the same. You have some other units here. To be perfectly honest, I don't anticipate us using this unit, or this unit. So I'm just going to jump down to the last three here. So this would be the equivalence of one atmosphere in newtons per meter squared. And remember we said that newtons per meter squared is the same as Pascal. So that's why we have these two numbers being the same. And then you can convert from Pascal to kilopascals, I'm sorry, by dividing by 1,000. So that's how we end up with one atmosphere is equal to, down here, 101.325 kilopascals, all right? So that's basically the relationship between the atmosphere units and the other units, all right? And these are also available in Canvas in that table that I provided for you. So you don't need to memorize these, all right? Okay, how do we measure pressure? Well, there are two instruments that we're going to discuss here. One is called a barometer, and the other one is called a manometer. The barometer is used to measure atmospheric pressure. And as we all know, the air that we breathe, right, the air that we live under, we are submerged in, is a mixture of gases, right? The main one being nitrogen, which is just under 80%, and then the next most abundant gas is oxygen, which is just like about 20%. And then you have some minor trace gases that exist. So the point is that these gases collectively, that mixture, which makes up the atmosphere, exerts pressure as well, like any other gas by itself, right? And the instrument that we use to measure the pressure of the atmosphere, which by the way changes, right, depending on the weather condition, right? So this is the instrument that is used to measure that. So the barometer, right, is what is used. And here is where we're going to get into this number here of 760 millimeters mercury. So as stated here, 1 atmosphere, by definition, is the pressure exerted by a column of mercury that has a height of 760 millimeters, all right? Now, oops, sorry about that. So basically, these are relationships between the atmosphere unit and the millimeter mercury unit, which is the same thing as the torr unit, which as we said before, is equal to 101.325 kilopascal. Okay, so this is the least sophisticated version of the barometer. In fact, the barometer would be this setup here on the right. But before we do that, let's talk about this setup here. So if you look at these two carefully, you see that the only difference between these two is that you have an open end here, where the top end here is sealed. The open ends are here and here, which are both submerged into the mercury, and mercury is the liquid of choice that is used for reasons which I'm going to mention later on. But before we get to that, let's talk about what's happening and what's the difference between these two setups. In this case here, because you have an open end here, the air can exert pressure on the mercury level inside here, right? Which would be equal to the pressure exerted on the mercury level outside of the tube. So they will equalize each other out, and therefore, as a result, the mercury level inside the tube will be at the same height or level as that outside the tube, all right? On the other hand, over here, the way this is set up is that you get a tube first, which is at least 760 millimeters long, right? And then, of course, you should be wearing gloves. You don't want to dip your hand into the mercury. You make sure you fill that tube with mercury. You put your thumb at the open end, and then you submerge it into the trough with the mercury, right? And then you remove your thumb. And then if the tube is long enough, what will happen is that the mercury level will fall to about 760 millimeters high. And this height here from the surface, I should say, of the mercury outside the tube. And this height here is actually proportional to the atmospheric pressure acting on the surface of the mercury. In other words, if on a particular day, the atmospheric pressure is greater, then the mercury level is going to be higher, and vice versa, right? So this is used as a proxy for basically measuring the atmospheric pressures, and that's where the 760 millimeter mercury unit comes in. So basically, based on this sort of setup, the powers that be, whoever decided these things, decided that 1 atmosphere is going to be equal to 760 millimeters mercury, right? So that's how we get that particular unit of measurement with respect to mercury. Okay, so let's look at this particular question. It says, a Canadian weather report gives the atmospheric pressure as 100.2 kilopascals. What is the pressure expressed in the torr unit? Well, if you remember, we said that 760 torr Oh, 760 torr is equal to 1 atmosphere, right? That's what we saw from, I'm sorry, not 1 atmosphere, I'm sorry. Well, it's equal to 1 atmosphere, but also equal to, which is what we need for this, 101.325 kilopascals, right? So in this particular case, and this is true, by the way, internationally, if you go to any country outside of the United States and you watch their weather reports, they tend to quote the atmospheric pressure in kilopascals. We here in the States, we for some reason stick to using millimeters mercury or torr. Okay, so basically you're starting off with 100.2 kilopascals, and you have to multiply by the conversion factor, which relates the torr unit to the kilopascal unit. So you're gonna put 760 torr here. And down here, 101.325 kilopascal below. And then we do the simple calculation. So 760 divided by 101.325. And according to my calculation, when rounded off to 4 figure, that would be 751.6 torr. So that would be the equivalent value in torr. All right. Any questions? Questions about this? Okay, manometers. All right, that's another instrument that is used to measure pressure, but this time we use it to measure the pressure of a gas. So if you have a gas in a container, basically we just attach a manometer to it, and that will give us the pressure of the gas. All right. Now, let's see here. Mercury again is a liquid of choice in the type of manometer that we're going to look at right now. And this is what we call a closed end manometer. Right? Later on, we're going to look at what is called an open end manometer, right? Now, in this particular case, you're going to have mercury inside here. Now, initially, before you attach or turn on the tap here, which connects the container to this part of the manometer, initially, the mercury levels will be the same on this side and this side. As you can see, it's a U-shaped tube, right? And then when you turn the pressure on, or you turn the tap on, then what happens is that the gas flows through and then starts hitting the mercury level here. So it exerts pressure here, right? And this, on this end, the mercury level is pushed up here, right? The difference in height between the two mercury levels, that is in effect equal to the pressure of the gas. So if you measure this difference in height in millimeters of mercury, then that would simply be the pressure of the gas. Now, if you want to calculate the pressure in pascals, then this is the formula that you would use, right? It is the pressure of the gas in pascals is equal to G. Now, I don't know how many of you have done physics before, but G is called the acceleration due to gravity, right? That's the acceleration that an object will have. Like if I were to release this and it falls to the earth under the influence of the gravitational field, then basically the acceleration experienced by that object will be equal to this value right here, which is 9.8 meters per second squared. The density, if you're going to use this formula, must be expressed in kilograms per meters cubed, and the H here, which is the same thing as the delta H here, will be equal to M, right? Or the units will be meters, all right? Now, basically what this is saying, going back to this diagram right here, what this is saying is that the pressure exerted by the gas here will be equal to the pressure exerted by the column on the point here, which is exactly at the same level as the mercury level on this side here, right? So if you draw a line here and you imagine something being here, then the pressure exerted by the column of mercury would be equal to delta H in millimeters mercury, or if you want to calculate it in pascals, it's going to be equal to this, right? So that's basically how the closed end manometer works. One thing I need to say before I move on, the assumption here is that there's a vacuum here, right? Which is effectively true, because when it comes to mercury, the vapor pressure exerted by mercury is very low. So you might have some mercury vapor here, but that would be very, very small, so much so that you can ignore it, all right? So that's what happens in the case of a closed end manometer. Now, in the case of an open end manometer, as shown here, where obviously the difference is that this end is now open to the atmosphere. There are a couple of things that you have to take into account. So the calculation for the pressure of the gas, or the determination of the pressure of the gas, won't be as straightforward as in the case of the closed end, right? So here we have two situations, right? In this situation here, the mercury level here on the open end is at a higher level compared to the mercury level down here, right? So what that tells us, that the pressure exerted by the gas on the surface here would be greater than the atmospheric pressure acting on the surface of the mercury on the other end, right? So this P bar here is the atmospheric pressure, also known as the barometric pressure. That's why they call it P bar, right? So basically, we can say that the pressure of the gas exerted here will be greater than the barometric pressure, right? And the difference between those two will be equal to delta H. So therefore, this is the mathematical relationship between the pressure of the gas and the barometric pressure. That is equal to, the pressure of the gas equal to the barometric pressure plus the delta H that is measured between the two mercury levels on either side of the U-shaped tube, all right? Now, in the case of the other setup right here, things are switched in that the mercury level here on the open end is lower compared to the mercury level on the end that is connected to the gas container. So what that tells us is that the barometric pressure here would be greater than the gas pressure here, and the difference between those two would be equal to delta H. So therefore, this is the equation for the relationship again between the barometric pressure and the pressure of the gas. The barometric pressure will be equal to the pressure of the gas plus delta H, all right? So that's the relationship between these two. So basically, in these setups, you have to know what the barometric pressure is before you can determine the actual pressure of the gas. You have to know the barometric pressure. You have to know, of course, the delta H, which you can measure, right? And then the difference between those two, in this case, would give the pressure of the gas. In this case, it would be the sum of the barometric pressure plus delta H that would give you the pressure of the gas, right? So that's basically how the open-end manometer works, all right? Okay, let me see what it says here. Oops, sorry. Okay, any questions about this? Any questions about the open end and the closed end manometer? Okay, so the next slide basically explains why mercury is the liquid of choice. All right, for those instruments, the manometer and the barometer. All right, mercury is very expensive. Okay, one might ask, okay, so why can't we use something more cheaper like water, right? Well, here you're going to see the reason why in this example. So this example says you have to calculate the height of a column of water, and they give you the density of water that exerts the same pressure as a column of mercury, and they gave it. Yeah, these scribblings that you're looking at here, this was from a video I recorded, so I'm just going to use these to answer the question, to explain how to calculate the height of the mercury column, right? So the formula, if you remember, I looked at, or I showed you before, is this formula right here, which is used to calculate the pressure exerted by a column of liquid, right? So just to remind you, the pressure is equal to the height of the column of liquid times the acceleration due to gravity times the density of the liquid, right? Now, according to the question here, the pressure of both the water column and the mercury column would be the same, right? So that's why I put PW, which is the pressure exerted by the water column, is equal to P mercury, which is the pressure exerted by the mercury column. So what I'm going to do now, for each of these terms, I'm going to substitute these terms with their respective expressions here, right? So H here becomes HW, which is the height of the water column. G is the acceleration due to gravity, which is the same, regardless. BW is the density of the water, right? And then that will be equal to the height of the mercury column times G, which again is the acceleration due to gravity, times the density of the mercury column. And then what I'm going to do, because the question is asking for the height of the water column, I'm going to isolate this on this side, which means I'll divide both sides by the density of water, right? And I'm going to end up with something that is cut off. Oh, wait a minute. Hold on. Get out of the okay, I'm going back to this. Okay, so basically it's algebra, right? Basically I end up with this equation right here. The height of the water column is equal to the height of the mercury column times the density of the mercury divided by the density of the water. And then I plug the numbers in, right? The height of the mercury column is 760 millimeters high, which is equal to 1 atmosphere that we talked about before, multiplied by 13.6, which is the density of the mercury, divided by the density of the water, which is 1.00 grams per cm cube. And when you put those numbers in, you're going to end up with 10,300 millimeters, right? So what this is telling us is that if we were to use water instead of mercury, you're gonna need a tube, which is at least 10,000 300 millimeters tall, which is about 10.3 meters, right? And just to give you an idea as to what we're talking about, basically my height is just under 2 meters, right? So you're gonna need a tube which is like 5 times my height, which would be, as you can imagine, is very inconvenient, right? So that's the reason why water is not used as a liquid of choice when it comes to instruments like the manometer or the barometer, right? We use mercury because basically, and mercury is basically the best liquid because of its high density. That's basically what it comes down to, all right? So it's like there's an inverse relationship between the density and the height of the column, right? So because of the high density of the mercury, then the height of the column for 1 atmosphere would be relatively small, and therefore it's more convenient to use mercury compared to water, all right? Okay, any questions about this example? Any questions? Any questions? Okay, so before we move on to the gas laws, we're going to start with the assignment for chapter 5. And I want you guys to focus on questions 1 and 2. Oh, wait a minute.
I got 2.
Oh, okay. Oh, it kind of fell thick. Yeah, just give it. Thank you. Again, for you guys out there in Zoom, let me go ahead and publish this assignment in Canvas. Let me go here. Now, your assignment number 5 for you guys out there in Zoom is now published. All right, so let's be. For some reason. Sharing. First, actually, number 1 should be relatively easy for you guys to do. It's a matter of just converting from 1 unit of pressure to another. So how would you do number 1A? they gave you 0.357 atmospheres. So what would you multiply this by in order to convert from atmospheres to torr?
760.
Exactly, 760 torr over 1 atmosphere. And so that's 0.357 divided by, or multiplied by 760. So according to my calculation, this works out to equal to 271. All right, so you should be able to do the others. I'm gonna give you a couple of minutes to do those, and then we'll move on to the next question. Yeah, you're right. You're gonna start off with the 745 torr. Right, so you're gonna start off with 745 torr. And then what were you saying is what you need? Small. Yeah, you're gonna put 101,325 pascals above, and down here 760 torr. And that's it, that's how you do that. Okay, are we finished with number one? So, let's look at number 2. So number 2 is basically similar to what we were just describing earlier. What I showed you in the PowerPoint. So it says the atmospheric pressure is 0.975 atmospheres. What is the pressure of the enclosed gas in the left arm of the tube in each case, in each of the cases below? So what they're saying is that in each of these cases, there's a gas that is trapped in the left side, here, here, and here, right? And in each case, the question is asking for you to calculate the pressure of that gas, right? Based on 2 things. One is the atmospheric pressure, right? And the other would be the height difference between the 2 mercury levels on either side, right? Now, in the case of the first tube, this would not be important because this end is sealed, right? So therefore, you won't have any atmospheric pressure playing any part in terms of the height difference between these 2 mercury levels. So therefore, the answer for this one, believe it or not, is that the pressure of the gas trap on the left side is simply 45 millimeters mercury. Right? There's no gas here, and there's only gas on the left side. So therefore, the mercury column here, the height difference would be equal to the pressure of the gas that is trapped on this side, right? Okay, so that's in the case of this setup. Now, in the case of this setup, obviously, this end is open. So you're going to have the barometric pressure acting on the surface of the mercury on the right side. Here, you're going to have the pressure of the gas trapped here, exerting its pressure on the mercury level here on the left side, right? And the height difference is 78 millimeters between those 2 mercury levels, right? So my question to you is this. What is the mathematical relationship, based on what we discussed earlier, between the pressure of the gas, the barometric pressure, and the height difference between the 2 mercury levels? You guys out here in Zoom, you can chip in as well, if you think you know what the answer is. What's the relationship between the pressure of the gas, the barometric pressure, and the H? What's the mathematical relationship? Pressure of what? Pressure of what?
Air pressure.
You mean barometric pressure? So you say P bar is equal to what? H,
G,
H plus what?
H, how is it plus?
No, I'm following what you're saying. I'm not-
H times G.
Oh, no, that equation I won't come into that. The equation will only contain these terms. Let me state that from the outset. Let me erase this here. So what's the mathematical relationship? You can look at what I just explained. Those diagrams I showed you with the open end manometer. The 2 situations.
Pressure gas,
Okay, so pressure of the gas,
the bar plus height.
P bar plus I. Now, why do you say that? Let me hear your rationale.
Well, I assume that we're trying to find pressure of the gas.
Right, I'm trying to find pressure of the gas, yeah.
So we take the pressure that we know and plus the height.
Well, it's more than just that. You see, as I said earlier, because the mercury level here is lower than this, what that tells you is that the pressure of the gas exerted here would be greater compared to the pressure of the atmosphere or the barometric pressure, right? So that means that for the mercury level here, the pressure exerted by the atmosphere plus the H here would be equal to the pressure of the gas, right? So that's why this is true. Now, to answer the question says, well, as you correctly said, the question says that you have to calculate the pressure of the gas. The barometric pressure is given as this, right? And the H is given in millimeters. So what do you think you need to do in order to add those 2 values?
convert the atmosphere to millimeters of mercury.
Right, so you have to convert the barometric pressure to atmosphere. How do you do that? So I'm gonna put 0.975 atmospheres, and we have to convert that to millimeters mercury. How do we do that? What's the conversion factor?
You do 0.975 atmosphere, and you do 760
Millimeters of
millimeters
mercury
mercury.
over 1 atmosphere, right? So let's see what that gives. 0.975 times 760, so that gives 741 millimeters of mercury, right? So basically, that's the value that you're going to use down here. 741 millimeters mercury plus H, which is 78 millimeters mercury. And that will give you the answer in millimeters mercury. So that's 741 plus 78. So that gives 819 millimeters mercury. All right, and let me just say that the question didn't specify the units that you need to find the pressure in. So what you could have done, and you get full credit if this was a test question, you could have converted the 78 millimeters mercury to atmosphere, right? And then add it to the 0.975. Different numbers, but basically the same result, all right? So that's how you do that.
You'd be subtracting it from the atmosphere, right?
Or you mean for this one?
No, for the second one, because you're starting off at 0.975.
Oh, right, my bad, thank you, yeah. Jump in the gun and think about the second one. So this will be equal to, no, wait a minute, we are subtracting. No, we're adding, I was correct. You're adding the 78. I see you're confusing them. You're adding the 78 because the pressure of the gas, that's what the question is asking for. The question is asking for the pressure of the gas, and that's equal to this, right? So the answer I got was 819 millimeters mercury. The subtraction comes in this case, right? Because in this case, the pressure of the gas here is less than the barometric pressure, P bar, all right? So basically in this case, P bar is equal to P gas plus the height difference. So in this case, P gas would be equal to P bar minus H, I'm sorry. So P bar is the same P bar that we're using from the previous part. And we subtract from that the H, which is 67 millimeters mercury. So let me see what that gives. 741 minus 67. And according to my calculation, this works out to be equal to 674 millimeters mercury. That's how you do that. All right. Any questions about this? Any questions? Any questions? Okay, so I think it's okay for me to clear this, right? So let me scroll down. Oh, okay, so let's go back to the PowerPoint because we can't do these questions yet based on what we've covered so far. All right, so next topic we're going to talk about, in fact, what we're going to do is get into some gas laws. And again, this is something that you should have met before, you know, different laws relating different properties to each other. And the first law we're going to look at is what is known as Boyle's law. And Boyle's law is the gas law, which describes the relationship between the pressure of a gas and its volume. Right? So there are different ways of expressing Boyle's law. This is one way. For a fixed amount of gas at a constant temperature, the volume of the gas varies inversely with its pressure, right? So basically what that is telling you is that basically as the volume increases, the pressure decreases and vice versa, all right? If you double the volume of a gas, then the pressure of that gas will be half, for example. If you triple the volume of a gas, then the volume or the pressure of the gas will be reduced to 1/3 of the initial value. Another way of expressing Boyle's law is this right here. For a fixed amount of gas at a constant temperature, the product of the pressure and the volume will be constant, right? So basically what they're saying is that the pressure times the volume is going to be equal to constant. And for those of you who enrolled in my lab, which I think is all of you except in one, you're going to see this at work in one particular experiment that we're going to do, which will be later on, where we look at the relationship. You're going to see actually quantitatively, when you do your calculation, that there is indeed an inverse relationship between the pressure and volume of the gas, right? So these are basically different ways of expressing Boyle's law in words. Mathematically speaking, you can express it this way. P times V is equal to a constant, or P initial times V initial is equal to P final times V final, or I prefer to express it this way. I prefer to express it this way. P1 V1 is equal to P2 V2. All right. So P1 and V1 will be the initial pressure and volume. P2 and V2 will be the final pressure and volumes. And let me just stress here that this law works when two things are held fixed. One would be the temperature, and two would be the amount of gas, right? So those are kind of like two constraints that have to be in place in order for you to observe the inverse relationship between pressure and volume, right? So that's Boyle's law. And this is basically showing you graphically how Boyle's law works. So what we're looking at here is on the plot here on the left, a plot of pressure on the y-axis versus volume on the x-axis, right? And this shows you, basically what I said earlier. If you increase the volume of the gas, everything being constant, then the pressure would be reduced. And that is seen here, where we're starting with a pressure of 4 atmospheres, where the volume is V, whatever V is, and then this person decided to double the volume, and there's a corresponding decrease to the same extent of the pressure, right? So the volume is doubled, the pressure is now to 2.0 atmosphere. And then if you double the volume further, right, from 2V to 4V, then the pressure will be halved again from 2 atmospheres to 1 atmosphere, and that continues, right? So you're going to end up with, if you were to do this experiment and plot your graph, you're going to see this curve, which approaches the x-axis but doesn't touch it, right? So that's what this is showing you. Now this on the right side is showing you the relationship between 1/P versus volume. And you'll notice it's a straight line, and that should come as no surprise based on the equation, because the equation is PV is equal to a constant, all right? So what that means is that if we do V is equal to 1/P times a constant, another way of stating it is 1/P is equal to a constant times V. So, you should be familiar from your math courses that if this is Y and this is X, which is what we have plotted here, then you're going to end up with a straight line where the slope would be equal to the constant, all right? But that's basically how that works. And this plot is more useful because you can answer questions like what is stated here. It says, estimate the pressure at 3V. Well, that's very simple. All you have to do is identify 3V here on the x-axis and then draw, using a ruler, of course, a perpendicular line like this, which touches the line, and then you find out what the value here is. And then it's asking also for 5V, where 5V would be about here, I would think. And you do the same thing, draw a line up, and then where it touches the plot, you draw another line horizontal to touch the x-axis, and then you can read off what this would be, right? And that's it. Okay, so that's Boyle's law. So now we're gonna look at an example, and you guys should be able to do this. It says you have a balloon that has a volume of 4.50 liters, where the pressure of the atmosphere is 748 torr. Assuming that the temperature remains constant, what would be the volume of the balloon when it is taken to a mountain resort at an altitude of 2,500 meters, where the atmospheric pressure is 557 torr? So the important numbers are the ones I'm circling. This is not really important because that doesn't come into play when you're doing the calculation, right? So if you recall, I said that P1V1 is equal to P2V2. That's the way of expressing, one way of expressing Boyle's law. So when you get a question like this, of course, you have to identify what is P1, what is P2, and so on, right? So based on the information I see here, V1 is the 4.5 liters. P1 would be the 748 torr, and this would be P2. And what the question is asking for? The question is asking for V2, right? So what I would do is rearrange this equation to get V2 is equal to P1, V1 over P2. And then we put the numbers in. P1 is 748 torr. V1 is 4.50 liters. And P2 is equal to 557 torr. And then we do the number crunching. 748 times 4.5 divided by 557. And according to my calculation, this works out to be equal to 6.04. And the final unit would be in liters. And that's what we do that. Right? So that's a typical Boyle's law type of question. And in your assignment, let me see here. Question number 3 is also a Boyle's law question. So based on what we have done here, you should be able to do number 3 in your assignment, right? Now, let me just say this. When using this equation, it does not matter what the units are for pressure or volume, as long as they're the same on both sides, right? So P1 and P2 could be in atmospheres, it could be in millimeters mercury, it could be in pascals, it doesn't matter, as long as P1 and P2 are the same units, right? And the same is true for volume, right? V1 and V2. They could be liters, milliliters, gallons, it doesn't matter, right? That's a key thing you need to remember, because you may be given a question. You may be given a question where, for example, V1 is given in one unit and V2 is given in another unit. So some conversion would have to take place in terms of transforming the unit before you plug it into the equation. Okay, so number 3 is not exactly that type of question. Number 3 is more straightforward. The only difference for number 3 is that they're asking for P2. So basically, you'll be using P2 is equal to P1 V1 over V2, right? So you just plug in the numbers into that equation, and that will help you to solve question number 3. All right. So I'll leave you to do that on your own, because I think that's relatively easy. Okay. Any question about this example? Any questions? Any questions? Okay. Another law. Again, this is something you should have learned in your previous chemistry experience, which governs the behavior of gases is Charles' law. And this law describes the relationships between the temperature and the volume of a gas. And again, we can express this law in words, which is what you see here on the screen. The volume of a fixed amount of gas at a constant pressure is directly proportional to, and this is very important, its Kelvin or absolute temperature, right? So in this particular case, it doesn't matter what units you're going to use in this case for temperature, right? The temperature must be expressed in Kelvin, all right? So if you're given like a problem involving this, where the temperature is given in degrees Celsius, you have to add 273 to it before you can plug that into the equation I'm about to show you, right? But before we do that, let's talk about this concept of absolute zero. Absolute zero is the temperature obtained by extrapolation of the graph you're going to see shortly to zero volume. And this is a theoretical concept. Basically, what that seems to suggest is that at that temperature, the gas molecules will have no kinetic energy, right? Typically, when it comes to gas molecules, the type of energy that they might have would be translational, which we talked about earlier, but you also have rotational and vibrational, right? But at this temperature, absolute zero, basically the molecules will have no kinetic energy of any type whatsoever, right? So the absolute zero on the Celsius scale is equal to minus 273.15 degrees Celsius, right? For all purposes, we're just going to run it out to 273, right? That represents the temperature at which you'd expect the gas molecules to have no energy, right? This has not been demonstrated, as far as I know. The last time I checked was last semester. Nobody has achieved absolute zero, right? So this is just an idea which predicts something that has not been proven, right? And one of the reasons why it has not been proven is because, well, firstly, nobody has achieved absolute zero. And the other reason is that if you even were to achieve absolute zero, when you take a gas and let's say you measure the volume and you cool it, right? And as a result of cooling, the volume will contract, right? After a time, you get to a temperature which would be the boiling point of that particular substance, right? And therefore, it's no longer gas if you cool it further because it's not a liquid. And therefore, you cannot take the same type of data points that you would have if it were gas at those low temperatures. And that's exactly what is shown here in this diagram right here, this graph, right? So what was done here was a plot of volume of the gas versus the temperature in Celsius, right? So this person cooled the gas and measure the volume, measure the temperature at each instant until you get to a point where it becomes a liquid, right? So therefore you cannot do the same data collection that you have done before. So if you draw a line continuing the trend, what you'll find is that the graph or the plot will cut the x-axis at the value that I mentioned before, which would be 273 degrees Celsius, right? And of course, that will be the point where the volume of the gas would be zero, if it were a gas at those low temperatures, right? So basically, as we said before, that is considered to be absolute zero, and this is basically the basis for the Kelvin scale, because, let's see here, right? Because the absolute zero basically was assumed to be 0 Kelvin, right? So therefore, 0 Kelvin is equal to minus 273 degrees Celsius. And in fact, the mathematical relationship between the Kelvin scale and the Celsius scale is that the temperature in Kelvin is equal to the temperature in Celsius plus 273. And in terms of the units, this would be degrees Celsius over Kelvin. And the temperature here will be in Celsius, right? So, no. Okay, hold on. I think I made a error here. Let me correct that. I'll look it up and get back to you on this one. So this is the relationship between the temperature in Celsius and Kelvin. Okay, where's the color? All right. Okay, so basically, if you were to use the Kelvin scale instead of the Celsius scale right here, this is the plot that will result. Okay, so this is the plot that you're going to end up with, right? If you plot volume versus the temperature expressed in Kelvin, and again, this will be 0 Kelvin. So basically, to get from here to here, all we did was move this axis over to 273 or minus 273, and that's how we get this right here, right? Okay. Okay, so let's look at, oh, and by the way, and I should have mentioned this earlier, the mathematical relationship between volume and temperature, according to Charles' law, let me write it here, is V1 over T1 is equal to V2 over T2. And for this to be true, the number of moles and the pressure of the gas must be constant. All right? So that's a mathematical relationship between the volume and temperature. Again, let me stress, the temperature must be expressed in Kelvin, right? Doesn't matter what the volume units are, again, because, if V1 and V2 have the same units, then that's fine, right? But the temperature must be expressed in Kelvin, all right? Okay, so that's Charles' law, which we can apply to solving this problem right here. So this question says you have a balloon indoors where the temperature is 27 degrees Celsius, has a volume of 2.0 liters. What would be the volume of the balloon outdoors where the temperature is minus 23 degrees Celsius, right? So one of the first things I would do is convert each of these to Kelvin. So the 27 degrees plus 273, that is equal to 300 Kelvin. And that would be my T1. And the minus 23, that would be equal to 250 Kelvin, and that would be T2. And then this volume here would be V1, and the question is asking for V2. Right? So remember we said V1 over T1 is equal to V2 over T2. So we need to isolate T2 by itself on this side. I would do that by multiplying both sides by T2. So therefore, these two will cancel out. So you're going to end up with V2 is equal to V1 T2 over T1. And then we plug the numbers in. V1 is the volume initially, 2.0 liters, multiplied by T2, which is 250 Kelvin, divided by T1, which is 300 Kelvin, and then we do the calculation. So 250 times 2 divided by 300, and according to my calculation, this works out to be equal to 1.67, and the units here will be liters, because these Kelvin units will cancel out each other, right? And that's basically how that is done. Right, any questions? Okay, so that is basically Charles' law. What time is it? Okay. I think we can do another law. So the next law we're going to look at is Avogadro's law. This law describes the relationship between the moles of a gas and the volume. Right? So in words, this is Avogadro's law. At a fixed temperature and pressure, the volume of a gas is directly proportional to the amount of gas in moles or to the number of molecules of gas, right? And mathematically speaking, we can express it this way. The volume is directly proportional to the number of moles, or the volume is equal to a constant times the number of moles, which can be rearranged to give you volume over the number of moles equal to a constant, right? Another way that it can be expressed, let me squeeze it up here, is V1 over N1 is equal to V2 over N2. All right, so basically, just like we did in the previous examples, if you're given 3 of these terms, you should be able to find the 4th one, right? Okay, so that's Avogadro's law. Now at this juncture, let me just say this. So you'll notice that in the case of Avogadro's law, 2 things have to be held constant. One is the temperature, and the other one is the pressure, right? So those 2 things would have to be constant in order for you to observe this law. So at this juncture, I want to introduce, or maybe I should say reintroduce, the concept of standard temperature and pressure, because in order to make meaningful comparisons between gases, some things have to be held constant, and temperature and pressure are usually the convenient factors that you can hold constant in order to make these sorts of comparisons. So the powers that be, whoever they are or were, decided that the standard temperature would be equal to 0 degrees Celsius or 273 Kelvin, and the standard pressure would be 1 atmosphere, which is of course 760 millimeters mercury. All right. So whenever you hear the term STP, you should immediately understand we're talking about those conditions. All right. Another thing I want to talk about here, which again you should have met before, is this concept of molar volume, which by definition is the volume occupied by 1 mole of a gas. All right. And it turns out that 1 mole of a gas will occupy the same volume at the same temperature and pressure conditions, right? And under STP conditions, it turns out that this can be shown by calculations, that the molar volume of what we call an ideal gas is equal to the value that you see there, 22.4 liters for every mole of the ideal gas, right? Later on, we're going to talk about the difference between an ideal gas and real gases. And pretty much between now and until we get to that topic, we'll be assuming that the gases that we're discussing are ideal gases, right? So that is basically the molar gas constant on the STP conditions. And this value is also provided in that packet that I've posted in Canvas, all right? Okay, so with that out of the way, oh, I thought I had an example. Let me see here. Okay, so number 5 is one in the assignment, is an example of Avogadro's law question. They gave you the moles, they gave you pressure. Oh, no, that's not. Oh, no, that's not it. That's not how it is. Okay, I don't have such a question here. Okay, maybe next class I'll be able to dig up some questions, or at least one question on that, so that you will know how to use that. All right, so that's a molar volume. Okay, one more law and then I'll call it a day. Gay-Lussac's law, which relates the pressure of a gas to its temperature, right? And again, you can express it in words. At a fixed volume and moles of a gas, the pressure of a gas is directly proportional to the temperature. Again, very important, expressed in Kelvin, right? In fact, let me just say this now. Whenever you're using temperatures for any laws or equations involving gases, the temperature must be in Kelvin, all right? So that is true for Gay-Lussac's law, that's true for Charles' law, that's true for any other law that you're going to meet later on. The Boyle's law does not have any temperature values or temperature terms, so that wouldn't apply. But pretty much for all the other laws and equations that you're going to meet in this chapter, you have to convert the temperature to Kelvin if it's given in Celsius before you can plug it into the equation, right? So mathematically speaking, you can express, Gay-Lussac's law. Pressure is directly proportional to the temperature, or pressure is equal to a constant multiplied by the temperature. And then you can rearrange this to get P over T is equal to a constant, which means that P1 over T1 is equal to P2 over T2, right? And that's basically how Gay-Lussac's law works. Again, the pressure units doesn't matter as long as they're the same on both sides, right? P1 and P2 must be equal to each other. Yes, ma'am.
Number 5.
Number 5?
It's 1 for moles.
Okay, I don't want to do number 5 yet because that would involve the ideal gas equation, which we have not touched on yet. Yeah. All right. Okay, I'm going to stop here for today. I don't think I have any announcements.
What are the 3 equations there at the bottom?
Oh, different ways of expressing.
Is that pressure at temperature or?
No, oh, I'm sorry. This is representing proportional to. I don't know if you're familiar with that slide.
No.
Right, it's
So,
actually, it should look something like this. Right?
okay,
So what that means is that, let's say you have A and B here. What this is saying is that A is proportional to B. Basically what it says is that if you double A, B doubles. If you triple A, B triples and so on. Right? Okay, any other questions? Any other questions?
so what is the C supposed to represent
A
there?
constant.
Okay,
Right, exactly. Let me just check something out here in terms of your assignment, because I think you guys submitted or should have submitted. Okay, so, let me set up a Dropbox for assignment 4. Right now. So, let me change this right here. That's the day. I'll give you until tomorrow. Because by now you should be able to finish that segment.
Tomorrow night, right?
Yeah,
Okay.
midnight, yeah. Okay, so let me do this. Available today until tomorrow. Okay, let me just say one more thing just to make sure everything is set. Okay. So that is set, so you can turn that in Canvas. And I think that's all I have to say by way of announcement. Of course, I'll be available today from 11 to 4. So if you have any questions, feel free to come to my office or talk to me. Let me get those persons who came in late. Amo is here. Let me see,
I'm also here.
go with, okay. And Spall. And I think that's it over here. Yes, ma'am. Yes, ma'am. Mhm.
I was looking at, the PowerPoint.
Okay.
And I don't. Find that some of it's out, but I was looking at it. It was-
Well, if you look at the PowerPoint, that was switched.
It was.
Right, if you look at it carefully, you see that it was switched. So that's why I focused on just going by this, right? So as I was saying earlier. Let's go. Let's go stuff. If you look at this one right here, right? Remember, the gas is trapped on the left side. In the PowerPoint, it was on the right side. So-
Wait, so it's coming from here,
Right, no, the gas that is trapped,
it's in there.
it's in this part here, this is the seam end, right? That's what the question says. The question says, what is the pressure of the enclosed gas on the left arm? So basically, this gas that is trapped here would be exerting the pressure here, right? So that's P gas, right? Then you have the barometric pressure, which is acting from the atmosphere on the other end, right? So as I was saying, just looking at this, because the mercury level here is lower than the mercury level here, that means that the pressure of the gas here will be greater than the barometric pressure.
Okay.
You see what I'm saying?
So-
And the difference between the two will be the H. You see what I'm saying? So that's why it is the pressure of the gas is equal to the barometric pressure plus the H.
So for like the equations, it's gonna be read like this.
Well, it depends on how the question is worded. That's why I went to the question first. The question says the pressure of the enclosed gas is on the left arm. So that means that the gas that is trapped is on the left side, which means that it's here, here, and here in each case. So that's
So
what,
if it was like on the right arm,
Right,
would that mean,
that means that, like, for example, in this case, if the gas was trapped here, right? That means that the pressure exerted there, and let's say this was open, right? Then the barometric pressure they are acting on that end, right?
so
So
it P bar?
the P bar is equal to P gas, plus it, yes, you're right, right. So you have to read the question carefully and understand, what is being asked, Don't just jump, because you saw what the PowerPoint says, you have to look at all the questions.
Yeah. I was just, yeah, like.
Right, exactly, right.
It's like they look the same.
Yep, it looks the same, but it's an inverse.
Thank you.
No problem. Okay, let's see here, let's not go all this. Take care.